is what I'm holding here. This is a piece of paper. But if you're thinking that this is also a picture of a mole, you're not wrong either. But here's the thing. We're not talking about these moles today. We're talking about another type of moles. The other mole is that we're going to be working on. Avogadro's number, aka 602 hexillion. But don't let that overwhelm you. It's pretty easy actually, because when you think about it, just think about it like you know how 12 is like a dozen, right? Well, just think about a mole as a 602 hexillion. Which by the way has 21 zeros trailing behind these. But anyways, that out of the question. It's time for me to talk about a little bit about the history of this, which I'm going to be referring for now as Avogadro's number, named after the famous Italian scientist that proposed the theory of it. Because you see, in the past, scientists were trying to find ways of weighing atoms. So they proposed in using hydrogen in trying to weigh atoms, but it didn't really make sense back then. So they spent like 50 years thinking, stroking their beards, trying to find the perfect solution, until one scientist named Frank Wilhelm decided to use oxygen instead, because it bonded very well with a lot of other elements, and it was stable. But be mindful, this is before isotopes were invented, so we don't really use carbon, we don't really use oxygen anymore. So everyone was confused and chaos erupted from that. So it took another 50 years of stroking their beards and thinking until they finally decided to go for carbon, which is as common as oxygen, but also pretty plentiful and stable. But also, as isotopes were known, they used carbon-12, the most common isotope of carbon, because all the other isotopes of carbon, such as carbon-13 and carbon-14, the only other two, are less common and much more destructive. Well, anyways, this is what has been used for atomic mass. And then if you're thinking, what does this have to do with mole? Well, you see, when they were trying to come up with a mole, they try to use it. They try to define it based off of hydrogen, again, but that was called Nennenleitungsstrom constant in German. But then due to the isotopes and all the other stuff I mentioned, they switched to carbon-12, and then it was renamed Avogadro's constant, which is the other name for Avogadro's number. But anyways, regardless of that, to give you a picture of like, well, how many moles of a thing there are, let's just say I have a mole of moles from earlier. They'll be enough to cover a cube that is exactly about 20,000 meters and have the gravity of Pluto. But those sea of moles aren't suffocating us. But to be mindful. Theoretically, if you can apply the same thing to jelly beans or candy, whichever one you think of, there'll be enough to cover the whole entire planet. And very deep. Well, and well, going back, moles, they seem like a very large quantity, yet they seem so small to us when we're using them in chemistry. Because, for example, I have this whole container of table salt here, and I also have this bottle of water. Let's suppose, though it's not actually true, that these have the same volume. And you're thinking, oh well, the amount of atoms and molecules are different. Guess what? You're wrong. You are wrong. Because again, going back to Avogadro, these moles, all of these have the same volume. If these have the same volume, then these will have the same amount of molecules, which, no matter how different they are. And actually the same goes for, like, well, pretty much every single atom in here, and molecule, and element. No matter the content, the quantity will always remain the same if they are the same. If the quantity is the same. So anyways, this will also be helping in another one of my problems I'm going to be doing right now. In which case we're going to be trying to find how many atoms are there in 0.25 moles of magnesium. Which by the way is over here as the second alkaline earth metal, and the easy way, and this part is very easy if you know how to use a mole. It's pretty straightforward. Just multiply this by Avogadro's number, which is 6.022 times 10 to the power of 23rd. And then after that, in the end, we get 1.51 times 10 to the power of 23 atoms. And
Right atoms? Atoms? Okay.
And yes, yes, this is how many atoms that are in there. It's just 0.25 moles of it. Which actually also I should mention right now is that their atomic mass also relates to the amount of moles. For example, 1.008 atomic mass units of hydrogen can also be translated into 1.008 grams of hydrogen. Just saying. This is equal to 1 mole of hydrogen. And as a clarification note, this is not an abbreviation of molecules. Be mindful of that. It's just a short way of trying to say mole because I'm just too lazy and just writing out moles and stuff. But anyways, back to what I was saying. 1.008 grams of hydrogen is 1 mole. The same goes for oxygen, which is 16 atomic mass units, which can be translated into 16 grams, and and in the end, also translate to 1 mole. And why? Because one unit of their atomic mass, actually, one atom that weighs the exact same amount as their accepted atomic mass is equal to 1 mole of them. Which then brings me to my next problem: calculating a molar mass of a compound. Because, thankfully, my thing just fell down. It's going to where it said. Let's say we have hydrogen peroxide, H2O2, and we're trying to find what is the molar mass of it. And well, remember how earlier I mentioned that that their atomic mass equates to 1 mole of them. Well, in calculating their molar mass, we use that here. So in calculating this, 1.0088 atoms, 8, which is the atomic mass of hydrogen, and we multiply it by 2 because there are 2 of them. The subscript represents how many atoms are in the equation. So then we add the atomic weight of oxygen multiplied by the amount, which then, after a long series of equations, would roughly lead to 34.16. I believe.
0.016.
And then after that, we find our answer. But now that we got through the easy stuff, let's actually go through the stuff that you actually have to do some work on. First off, thinking back of earlier, let's just say of the amount of hydrogen peroxide we have 17 grams. How many moles are there in this? Well, using what we found earlier on the molar mass, which again is 34.016, we put the amount of grams there are, and we divide it by the molar mass. And then I'm gonna let you figure out the answer for this, but the answer will equate to how many moles are there, because just mind you, when you're dividing this, molar mass is grams per mole, and due to this you can cancel out the units, so there are just lots of mole, but I'm gonna let you answer this.
17 with the 34, 1/2 about.
Yeah, I'm going to leave everyone else to answer this. So this is for you to answer. It's your homework. But one last thing, if you're wondering about how we should do like the reverse, converting moles to grams using molar mass, it's easy. It's easy. You just take whatever molar mass you have, take whatever amount of moles you have, and you multiply them by the amount of by the molar mass, and then ta-da! You got yourself your grams. Oh yeah, by the way, this is not the answer to this. It's for you to do. Anyways, thank you for watching this video, and big shout out to Tyler DeWitt for inspiring me to do these videos. I really wish you still did those videos, but I would like to say good luck on making that biology virtual reality project on exploring the inside of a cell. I'm really looking forward to it. Anyways, thank you for watching that video, and if you're interested in this video, please subscribe, and we'll see you next time. Goodbye.